Hi everybody, welcome back. So today I'm going to be continuing the lecture that we had, well, I would say yesterday, but I guess for many of you it might not necessarily be yesterday, but on building quantum computing kind of from first principles. So what we'd done previously is we had begun talking about ordinary irreversible computing, and then showed how we can manipulate this in order to come up with a special case for it called reversible computing. And ultimately, where we're going with this is that we're starting with reversible computing and then transitioning over to quantum computing as a generalization of reversible computing. Now, for those of you who would like a written resource to go along with, I did some scouring, and the presentation that I'm doing is actually pretty similar to a presentation that Nielsen and Schwang end up giving in section 3.2.5 of their textbook. So if you're looking for, another version, and perhaps even a more complete version of what I'm presenting, I really strongly recommend that you take a look at that chapter. It's a fantastically written part of the book. But in any case, just to remind you about where precisely we were, let's go over and start everything up. So the key thing that we were doing is we were trying to translate the language of computing over from the strictly kind of bit-based version that everybody normally thinks about to this kind of linear algebra language, because of the fact that the linear algebra's version or vision of computing is going to actually transfer a lot easier over to quantum computing than the strictly kind of bit-based version that mostly we think about. So the fundamental idea behind all of this is this idea of a one-hot encoding, which, as you remember from last time, is a form of a unary encoding of a number. So, for example, we would write the number 0 in one hot as something like this. And 1 would be written as 0, 1, 0, and 2 would, of course, be 2. Or, no, it wouldn't be 2. It would be 1, 0, 0. Okay, so that's an example of a one-hot encoding. We can also express this in linear algebraic language by noting that each of these represents a unit vector and an orthogonal unit vector. So we can end up translating that over to, for example, the vector 1, 0, 0, which I'll call E0. Now, I didn't introduce this language last time because I thought that, front-loading notation is a sure way to get everybody confused. But now that we've spent a little bit of time with this formalism and this language, I'd like to introduce a little bit more language on top of it. So these vectors, these unit vectors over here, E0, E2, and so on and so forth, they are all orthogonal and they end up forming a basis. And this basis, formed by E0 and E1, we'll call the computational basis. And EI is a computational basis vector. Okay, now this language isn't going to be super important at the moment, but as the lecture continues on, it's going to be increasingly important, especially as we transition over to quantum computing. So that's basically that. And now, once we have this over here, we can now actually begin to think about operations in an entirely different way. Like, again, as I showed you last time, we can actually end up encoding an operation like the NOT gate over here as just a matrix of the form E naught transpose, not E naught, E naught transpose, not E1, okay, and using the fact that, for example, for the NOT gate, Naught maps E naught to E1 because it flips the bit, and it maps E1 to E naught. And so therefore, the matrix representation for this, now using this new language, the matrix representation in the computational basis for the NOT gate is then 0, 1, 1, 0. Okay, that's it. So that is how we can represent matrices, and are all operations that we're used to as matrices. And so the question is, well, really, what kind of is what's the linear algebraic structure of these reversible operations? And now, if you recall, a reversible operation, I basically said, is an operation that we can invert. Okay, so reversible implies invert. And something like the NOT gate, you can very easily see that the NOT gate is clearly reversible, because if you apply NOT twice, you end up getting the identity. All right? But that's kind of, I think, not a very accurate definition of what we exactly mean by a reversible model. So let me give you the following formal definition of what I mean by a reversible gate set. So in particular, let's define the following. Let E0 through En minus 1 be computational basis vectors. Then let the set of Gj over here be a set of transformations on E naught through En minus 1, such that for all E sub k in the computational basis, and for all j indexing one of the sets of transformations that's in our gate setup here, there exists L such that G sub j acting on EK equals EL. All right, so let me just be clear about exactly what I'm saying so far. What I'm saying is that for every gate, we can feed in any basis vector we feel like, and we're going to get another basis vector back out. So by this, what we mean is we are demanding essentially that the domain is the range, so that all basis vectors that we start with are mapped to new basis vectors under this transformation. And because each basis vector corresponds to a number, all this is really saying equivalently is that our function ends up taking some sequence of bits and mapping them to a new sequence of bits. It's just we've expressed this in linear algebraic language now. Now, what we end up saying is we say that the set G sub j is a reversible gate set if for all sequences mapping the positive integers to a index for this over here, and an integer m, which is greater than 0, there exists a new sequence, S prime, that maps positive integers to the set 0 through n minus 1, and m prime greater than 0, such that GM GSM minus 1 all the way to GS0 acting on, or sorry, actually I want to write this the other way around. My apologies. Such that GS prime M prime minus 1 going all the way down to GS prime 0 times GSM minus 1 going all the way down to GS0 EK equals EK. All right, so in other words, these two operations over here form the identity, i.e. they do nothing. So another way of saying this is that for every sequence of gates that we can take from our reversible gate set, there's some other sequence such that that other sequence of gates exactly cancels it out. Now, there was a question that was raised the other day about whether invertibility ends up applying this, implying that we've got a reversible gate set. Actually, technically speaking, no. We need to ensure that our gate set is more than just invertible, but also that the inverse operations can be implemented inside the gate set that we have. There are some circumstances where it's conceivable that you could have operations which may not necessarily be in your gate set, but would be needed to invert the gate sequence that you have. So that's why we need to be, I wanted to be very careful about the specification. So a reversible gate set is a set of gates where you can invert, but the inverse also is a sequence of gates that you can express inside the gate set. Okay, and that's basically that. So here's an example of this. Let's consider the case of, not and Toffoli. Okay, so I mentioned last time that not and a Toffoli gate are a universal gate set. And again, the idea of the Toffoli gate is it's a reversible AND gate. So what we've got three inputs over here, A, B, and C, going into the Toffoli gate. What it does is the Toffoli gate doesn't do anything to the first two inputs, and the third input, it will exclusively OR with the AND of A and B. Okay, so that's again how the Toffoli gate works. Now, we showed last time that not squared is the identity gate. Similarly, we showed that the Toffoli squared is also equal to the identity gate. And so what this means is that both of these are invertible. And also, what it ends up meaning is that if we have a gate set, G sub j, that consists of every NOT gate, i.e. not acting on the 0th qubit, all the way down to not acting on the last bit. Sorry, I said qubit there. I'm putting a cart before the horse a little bit. I apologize. So, the next thing that we need to do for this is we need to think about, a sequence of gates. So let's say what we've got is we've got some particular sequence of gates, S 1 through S M or S0 through M minus 1. Or these are going to be sequences of different indices for these NOT gates, as well as, Toffoli gates, which now might be of the form, for example, Toffoli acting on 0, 1, 2, 3, so on and so forth, all the way down. Okay, so we've got some sequence that on an indexing of all of these gates in our gate set. And so what we have is we have that GSM minus 1 over here, GS0 would be the sequence of gates that we are actually implementing that are indexed by this over here. Okay, so this is a sequence of gates that we want to implement. We can apply the inverse of this by basically just multiplying over here the following. We multiply this by GS0, GS1, going all the way down to GSM minus 1. Well, why is that? Well, if we left multiply this by that, then you'll notice that because every gate in this gate set is a squares to identity, GSM minus 1 over here is going to cancel with this one. And then we're going to continue to telescope through the entire series where everything ends up canceling between both of them. So this is equal to identity. So therefore, NOT and Toffoli, by the above definition, form a reversible gate set, because every possible sequence of these gates can be inverted in there. And then, using the argument laid out by the Bennett trick, we can see that this is not just a reversible gate set, it's also a universal gate set. Okay, so that's cool. Hopefully that'll give you a bit more of an idea about, how in principle we can kind of lay out and think about reversible circuits. But actually, there's kind of just a little bit more structure that I'd like to get into regarding reversible circuits before we start kind of moving on. And that's actually that all reversible circuits, if you notice, they seem to be kind of, there seems to be some suspicious stuff about them, right? In that the two most natural examples that I gave you squared to be the identity. And last time I showed you some other examples, like, for example, the controlled NOT gate and others that also squared to identity. And every single one of them that I ended up showing has the following property, that there's always one non-zero matrix element in every row and column of the matrices when they're expressed in the computational basis, where again, the computational basis is the basis spanned by E0, E1, all the way down to the last vector. So, the question is this a coincidence? Well, the answer is no, it's really not. Actually, what ends up happening is that it turns out that reversible operations acting on finite dimensional spaces will always actually end up giving you matrices of this form. And in general, they'll always actually be permutation matrices. And we can actually prove this. So, claim all reversible gates acting on a finite dimensional vector space or can be represented as permutation matrices. Okay, and the intuition behind this is actually really kind of clear. The intuition is that we demand that all of our gates be reversible, right? Which means that they're carrying out a one-to-one map. So that means for every input basis vector that you feed in, you're going to get a single basis vector popping out. And so, because you end up getting that, you can actually view the transformation that the gates are doing as actually just a relabeling of all of the basis states. So it's perhaps no surprise whatsoever that that all of these are actually just permutation matrices at the end of the day. But I'll give you a little bit more of a formal argument behind this. And in order to get the formal argument, again, I just want to remind you of a couple of facts from linear algebra. The first fact is that any gate or any matrix in general can always be expressed in a computational basis as the following. It's always E naught tilde G E naught transpose G E1 going all the way down to E naught transpose En minus 1, again for an n by n matrix, going all the way down to En minus 1 transpose En minus 1. Okay, so that's the first thing, that we can always represent it like this. It's going to be convenient for me to also use another representation for a matrix. This is a kind of a more algebraic definition for the matrix. So we can always end up expressing a matrix as the following. We can always express it as a sum over J and K of okay. Now, you can see immediately that if we end up, say, taking EQ transpose G R over here, then what we'll end up getting is that this is actually equal to sum over J and K of EJ transpose G EK, just like before. But again, remember that we've got an orthonormal basis here. So because we've got an orthonormal basis, the inner product between EQ and EJ is the Kronecker delta function, EQJ. Similarly, ER and EK is delta KR, right? And so then, using the fact that the sum of the Kronecker delta function just ends up giving us the function evaluated at the point, this is, of course, EQ transpose G E R. And so, as you can see over here, both representations end up giving us precisely the same value. And so if two things will have precisely the same matrix elements, they're the same object. So this is an equivalent representation here of this matrix up there. But it's kind of more convenient to deal with under some circumstances than the others. Another property, a fun fact for you to remember, is just a few properties of the transpose operator. So the transpose operator, if you've got any two matrices, A plus B, and we transpose the sum of them, that's actually equal to the sum of the transpose. All right. Another important property, and this one is going to get generalized a little bit later on in the lecture, but the product of two matrices, if we want to transpose that, that's actually the transpose of the product, but in the reverse order. Okay, so those are some properties that are really important for you to know for much of the linear algebra that'll show up here. So, okay, cool. So now that we've done that, let's move forward on the actual proof. Okay, so if G is reversible, then G inverse exists. Okay, cool. And furthermore, what this means is that because all of the gates in a reversible gate set will end up mapping EK over here to E, let's say R. Then, similarly, G inverse will end up mapping EP to ES, right? So basically all that I'm trying to say here is that the inverse also, not apart from it existing, by definition, that inverse also has to yield elements that are in the same set. Okay, fantastic. So if it's reversible, now let's take a look at the matrix elements, right? If we look at a single row of G, right? Row K, say. That row in the matrix will end up looking as follows. All right, wonderful. So that is basically the form. And so now, what I'm going to do is I'm going to make a couple of claims. First off, assume for all L EK transpose G EL equals 0. Okay? So what I'm essentially assuming here is, for the purposes of contradiction, let's assume that every single one of these elements up here was precisely 0. Okay? Well, if it's precisely 0, then obviously we've got a problem. And the problem is basically that if we're going through, then we know that this implies that for all L, G acting on EL has to be not equal to E sub k. Because if any of them were equal to E sub k, well, then E sub k transpose acting on it would give you one inner product. So there cannot be any one that ends up mapping to that. All right, cool. But G over here is invertible. And that implies, under these circumstances, that it's a 1-to-1 map. Okay? So, it's a 1-to-1 map. However, the dimension of the domain of G is equal to the dimension of the range of G. Ergo, it's impossible that the function can take every input, map it to a unique output without having every single element represented. Ergo, there must be at least one non-zero element. Implies number of non-zeros has to be greater than or equal to 1. All right, cool. So now, let's, again, make an argument by contradiction. Let's assume that what we have is we've got two elements in a given row. Let's assume that E sub k transpose G acting on EP is equal to E sub k transpose G acting on EQ equals 1, and that the two are distinct. And so EP, so let's say, I'll write this as follows, is equal to 0, i.e. both of those vectors are orthogonal. Okay, cool. So if that's the case, then we know that since all of the vectors are orthogonal, then we can end up saying, okay, well, G E sub P has to equal to EK, which has got to be equal to G EQ. All right, cool. Now, if G is invertible, this has to imply that EP equals EQ, which is a contradiction with that. Ergo, number of non-zeros in every row is equal to 1. Now, we can go forward a little bit more and actually apply the exact same argument to the columns. And this ends up saying that each column has one non-zero matrix element. So this shows that, for example, the types of matrices that we can have representing reversible gates will always be of the form, say something like this, or for a three-dimensional case, we might have something like 1, 0 over here. Okay. Or we might have something like 1, 0, 1, 1, so on and so forth. You get the idea. But the point is that these matrices over here, you can see if what we do is a matrix is a permutation matrix, if the rows can be permuted to form identity. Okay, and it's clear that if our matrices have only one non-zero matrix element in every row and column, we can just swap the row with the corresponding one where that element would be normally. Like for this one over here, we could swap position 3 up to position 1, position 1 to position 2, and position 2 to position 3. Okay, so this can be permuted, i.e. the rows can be relabeled in order to make the identity matrix. And in general, we can do this with every matrix that has exactly that property, just by transposing the row into the corresponding location that it would need to be in to make that element diagonal. Okay, cool. And so that ends up showing that actually every single matrix, every function that you can carry out on a reversible computer is actually just a permutation. And this is also fascinating because what it shows is that we have this universal model for computing, right? Because we mentioned that we can implement a universal gate set like NOT and AND on this over here and view it actually entirely as just a permutation, which is, I think, super cool. But actually, there's another structure to this that is actually, I think, really quite interesting. And this is going to show up intensely once we get to quantum computing. But claim is that if G is reversible, then actually G transpose is equal to G inverse. So actually, if you jump back and think about the example that we went through over here, Where is that example? With the telescoping sums. You'll note that we formed the inverse basically just by taking this sequence and running it in the opposite order. But using the fact that A times B transpose is equal to B A transpose, we have that for gates like this that are their own transpose and inverse in this case, that this over here corresponds to that exact same rule, that transposition ends up making the inverse. So we can see that's a particular example, but the point of this claim is to say that this holds in general. In linear algebra speak, what this implies is that G is unitary. And I'll give you a bit better of a definition of what a unitary matrix is right now, or later, but right now it's kind of a little bit of a red herring. See it as some foreshadowing. So, the, like snow on the Iron Throne. But anyways, the way that we're going to deal with this is, again, using the properties of the transpose that I showed you earlier. So the way that we're going to do this is, okay, let's say that G is reversible. We showed previously that it is a, if it's reversible, then it's going to be a permutation matrix. It'll be something like this, right? Well, we can express this intuition by using this algebraic form for expressing a matrix as a sum of projectors over here. Because the matrix elements in every row and column for the projector matrix, for the reversible operators we're taking a look at only contain one non-zero matrix element per row, we could simplify that definition. And we can actually just write this as a sum of only over the non-zero elements. And so we can write this actually as just the outer product. And I just want to make sure that I get the index right for this. Yep. Of EX and E transpose f of x, where G colon EX maps to EF of x. Okay, great. So that is the function that we're taking a look at. So I think I might have gotten that mixed up. I think that I mean E f of x over here and E transpose x there. Okay, my apologies. So, in any case, this is the form of the matrix that we're taking a look at. Now, that's equal to G. So let's look at now G transpose. Okay, that is equal to sum over x, E f of x, E x transpose, all transpose. That, using the fact that the transpose of the sum is the sum of the transposes, we can write that as E f of x, E x transpose, transposed. All right, great. Now we just have to use our final property of transpose, which is that this is equal to the sum over x of EX, transpose, so the transpose goes away, and E f of x transpose. Okay, fantastic. So now, let's write this all out. So then, what is G transpose acting on G? That we can just write as a sum over x and y of EY, E transpose F of Y times E transpose, or no, sorry, it's E F of Y, E Y transpose. Okay, cool. Now remember that this is the function over here is 1-to-1. So therefore, this part over here ends up giving you, well, just sorry, this is it should be an x there. This should be delta xy. So when we use a property for the Kronecker delta, this ends up just becoming the sum over x ex transpose. All right, cool. And so savvy people in the class right now might look at this and say, "Hey, that's the identity, isn't it?" And yeah, it really is the identity. But in order to see this, what we need to do is we need to just take a look at what the matrix elements of this guy are. So the easiest way to see this is just to say, okay, well, let's say that we've got G transpose G acting on an arbitrary input computational basis vector, EK, over here. That will end up giving us a sum over x, EX transpose, EK. But again, because of the inner product property, that is just the sum over x, EX of delta xk, which is, of course, EK. So what this is saying is that G transpose G is a map that for every input maps the input back to itself. Ergo, by definition, this is the identity operation. Ergo, G transpose is equal to G inverse. And there you have it. That ends up showing that all reversible functions can be inverted, actually just by taking their transpose. Which again, isn't terribly surprising when you take a look at some of these examples over here, right? If we transpose, well, unfortunately, I guess all the ones that I drew over here are self-inverse. I guess this one isn't. But in any case, the fact that the transpose ends up giving us the inverse is something that we're going to see is very cool and reminiscent of what happens when we transition from classical computing to quantum. But in order to be able to do that transition, we're going to actually need to generalize one other thing. And I alluded to this last lecture, which is we're going to need to add some notion of probability or distributions over the different values of the EKs. So now let's generalize this to probabilistic reversible computing. Okay. So the way that we're going to do this is we're going to follow exactly the same formalism that we had over here, but instead what we're going to do is we're going to allow the bits that end up coming in to be probabilistic rather than deterministic. You might think, hey, well, aren't there more probabilistic things you can do? Like, couldn't you do something like, flip a coin and heads goes to a NOT gate? Well, we can actually simulate these sorts of protocols over here inside this framework where we have random inputs by doing the following. Let's say we've got a bit over here, which is probability of 0 equals 1/2, and the probability of 1 equals 1/2. If we do a controlled NOT gate, which is often denoted like this, between the top and the bottom over here, this is some value A, then we're going to end up getting a distribution on this bit over here, which is the probability of A is 1/2, and the probability of not A is also 1/2. So you see that what we can do by adding a source of randomness in the form of another bit and using controlled reversible operations, like a controlled NOT gate, or its doubly controlled version, the Toffoli gate, we can actually end up simulating this exact same protocol where, we're non-deterministically implementing gates. We just do it with extra memory. Okay, so that's the idea. Let's just focus on the case where we have a distribution over the inputs to our machine. And so now the natural way of doing this is to think about a probability vector, okay? So we can end up saying now that our computational basis states before for our inputs, we would always be able to form like E0, E1, all the way up to En minus 1, okay? Those would always be our inputs, but now we're allowed distributions over it. So we can end up saying like E0 with probability P0, E1 with probability P1, and so on and so forth. Okay, so that's cool, but it actually turns out that the notation that we developed previously for reversible computing does a beautiful job of actually integrating this as a single vector. Because if we go back, right, note that there's a ton of wasted space in our representations that we had here, right? Because we used unary encoding, like we're recording E0 over, in this case, using 3 bits. We don't need anywhere near that in order to be able to record it. In this case, I guess we need to, and you get the idea. So we can use that extra space to our advantage. And the way that we're going to do this is we're going to end up defining a distribution. I'm going to call this distribution psi for reasons that I'm sure every physicist here knows immediately. But I'm going to define our distribution over the vectors in the following way. Let's define the distribution to be the sum of px over here, ex, where the sum over x, px, equals 1. All right, cool. So now, if we have this, we can also imagine representing the probability distribution over the e-axis just by expanding out each of these e-axes. This will end up giving us just p0, p1, all the way down to pn minus 1. So that's actually really cool because now you'll note that all this extra space that felt like it was wasted when we used this language to talk about reversible computing now actually is relevant. All of it is being used because, in some sense, the probability distributions over these values are exponentially larger than the set that we had to begin with. So that is basically the way that we end up representing it. Similarly, we can end up figuring out what a probability is just by looking it up on this table. Well, okay, that's pretty easy, but we can do this using linear algebra by saying, okay, well, P0 is just the 0th element in this. So that is just given by E0 transpose acting on psi. And in general, the jth probability over here is just EJ transpose acting on psi. All right, Cool. So this gives us a way of actually concisely writing down a probability distribution if we've got a non-deterministic inputs into our machine, and computing what a probability is, just using an inner product over here. Okay, and this is, again, just taking advantage of the notation. There's nothing really deep about this whatsoever. Things get a little bit more interesting, though, now that we've done this, because we can start asking, well, all right, well, what are these reversible operations doing to these distributions? So imagine what we've got is we've got a reversible operation, G, acting on psi. Okay? First thing that I think is really kind of cool about this is that because each G acting on psi is just a permutation, interestingly enough, all reversible gates acting on a probability distribution of this form doesn't change the information or the entropy of the probability distribution that you have. Okay? And this is actually a direct consequence of the definition of what the entropy is. So the entropy, which basically ends up giving an estimate of the total amount of information needed to code this probability distribution, is given by S, for the Shannon entropy, is the sum over J, Pj, I'll put a negative here, log Pj. Okay, so that's the Shannon entropy. And my claim is that applying G to psi doesn't change this. Okay, well, let's define then, if we go through this, let's say that G maps EX to EF of X. Okay, so if we end up doing figuring out the entropy for G acting on psi, then I'll have this new entropy, which is negative sum over J, or I'll write it in terms of X here, P of F of X log P of F of X. All right, cool. But again, because of the fact that F of X is a reversible function, and it affects, because it's in a finite dimensional space, a one-to-one map. What we can do is we can actually just rewrite this by rearranging the sum as sum over X px log px, and that is equal to S. So what this means is that if we start with a distribution, right, that has a fixed value of entropy, say S0, S1, then the gates in a reversible gate set cause us to just transition to different points in this space of equal entropy. And none of these operations whatsoever can possibly change the entropy. Okay, cool. Now, that's kind of wild, I think. But there's actually one operation that can be viewed as changing the entropy. Now, it's somewhat optional in this case, but I think it's kind of useful. And that operation is measurement. So if we think about what it means when I talk about one of these probabilities, it means that I'm allowed to draw a sample from the distribution. And at that point, when I draw a sample from the distribution, I no longer can view it as a distribution. I know what its value is. So in a sense, it becomes that value. So if we define an operation M, now this M is a nonlinear operation that cannot be conveniently expressed as a matrix. This operation M, what it will end up doing is it will end up mapping psi to E0 with probability P0 and down to En minus 1 with probability Pn minus 1. Okay? So you'll note now, once you've done a measurement, right, instead of the distribution being psi to begin with, which is P0 all the way down to Pn minus 1, what we end up getting is this. If we measured E0, then we will literally just get that popping back out. Now, if we compute what the Shannon entropy is for this guy, Shannon entropy is negative sum over x p x log px. And that, if we use the convention that 0 log 0 equals 0, then the Shannon entropy is equal to negative log 1 equals 0. Great. So what this ends up saying is that measurement actually, from this perspective, what it does is it ends up, if we view this kind of in reciprocal and view this as the 0 entropy ring up here, where, you know, you would have like E0 maybe here, E1 there, this would end up mapping you back up to these vectors over here. Okay, so measurement is the only thing in this theory, or this model of computing, that actually allows you to change your entropy. So that's what you can use in order to suck information and or entropy out of the system or put it back in. The final thing that I want to mention about this is, and this part is somewhat trivial, but it's actually kind of interesting because it will create a contrast between this and the quantum theory that I'll be talking about shortly. One thing that you can do is you can note that if we've got any state psi over here, we have that for any reversible operation, we have mg psi is equal to gm psi over here. So what this says is, this says, well, measurement, it kind of is an operation in the sense that, you know, it changes our description of it. The probability distribution that we end up getting out of this is independent of whether we measured earlier or measured later. So from that perspective, measurement is kind of a irrelevant feature of this theory. And so in order to see this, okay, let's just take a look at the first side, right? We've got mg psi. Now, again, g, let's assume that it'll map ex to ef of x. And so what this means is, this means that this will output a probability distribution that will be ex with ef of x with probability px. Okay, cool. So now let's take a look at this distribution. What this will do, m psi, when we apply that, what it'll do is it'll output g acting on ex with probability px. Now, because g, again, is a permutation on this, it will end up mapping ex, again, to E f of x with probability px. And this implies that we have exactly the same probability distribution. Ergo, when we repeat this experiment a large number of times, these two distributions cannot be distinguished. And so they're the same distribution. Okay, so we've got these two distributions and they are exactly the same. And so what that means is that the order of measurement really doesn't matter at all. Now for quantum computing, that's going to be entirely incorrect. So, well, without any further ado, let's actually start quantum computing. Okay, so it might come as no surprise that basically you've already learned most of the formalism that you need in order to understand what quantum computing is, okay? So the first thing that we're going to do with quantum computing is we're going to change the definition of our states. So in quantum, what we have is in classical, what we have is we've got our vector psi, right, which is a probability vector. It will have probability p0 going all the way down to pn minus 1. In quantum theory, which is kind of the formalism that we use in order to describe quantum mechanics, we have a very similar description. However, in the quantum case, our state, often called a state vector, is of the form square root p0 e to the I theta 0 square root pn minus 1 e to the I theta n minus 1. Okay, and we can end up seeing from this that the probability here ends up equaling the square of, let's say, pj equals psi j squared. So what this is over here an L2 normalized probability distribution. So what I mean by that is that it's not like an ordinary probability distribution, right? Because we've got these funky things over here. These things are complex numbers, but they're unit length. So each of them is some value on the unit circle, where this is the real part, and this is, like, let's call it x. Let's call that IY, all right? And these points over here correspond to x squared plus y squared equals 1. So all of these values, e to the I theta, will correspond to a different unit phase. So it's kind of like the equivalent, again, of a sign that we have here. So for real numbers, we would only have 1 and minus 1, which are these 2 points on this side. But in general, in quantum theory, we're allowed to have anything we feel like. It's just that our probability now, the sum of the squares has to be equal to 1. So in particular, we've got sum over j, absolute value of the jth component of psi squared equals 1. Okay, so that is how that goes. Another way of writing this is that we can write psi transpose psi is equal to 1. Great. So all of these vectors over here actually, this is the part, one of the things that I think is really cool. All of these vectors over here are, in quantum theory, they're all unit vectors. Okay, so our set of valid distributions are all, well, sets of unit vectors. And unlike the purely reversible case, we're not limited to just having discrete vectors that end up looking like this. You know, these are subsets of those vectors over here. We can have distributions with them, and we can have different signs. It turns out, actually, that all of the power of quantum computing doesn't come from the large number of components in these vectors, like many people say. It actually comes in because of the subtleties of those signs. And we'll get into that later. But that's something to bear in mind. So that is how we end up going about and formulating it. Now, there's a few other things that need to change, right? I actually said psi transpose psi is equal to 1. That was a little bit wrong. Because in quantum theory, we've got to worry about the fact that there's complex elements. They're not strictly real like they were in the case of the probabilistic reversible computing. So what we need is a slightly more sophisticated adjoint. So instead of the transpose, what we need is a Hermitian conjugate, or conjugate transpose, or adjoint, which is represented by this dagger symbol up here. Okay? And what this means is take the conjugate transpose. So that is equal to, for psi dagger will be its transpose. So it would be, for this example of psi up here, it would be P0 e to the negative I theta, because, again, taking a complex conjugate causes the sign of I to flip. Well, I think you might also need Cauchy's identity in order to be able to do that. But in any case, this ends up getting Pn minus 1 e to the negative I theta n minus 1. And you can see that once we've done this, using the fact that e to the I theta x times e to the I theta minus x equals e to the I theta x minus theta x equals 1. So when we take this inner product over here, you note that the signs, or the complex phases that we end up getting, cancel. And we end up getting that psi conjugate transpose psi is then just equal to the sum over j, pj, which is equal to 1. Okay, cool. So that vindicates the unit norm behavior. Now, the conjugate transpose, it behaves actually just like the transpose does. The conjugate transpose of the sum is equal to the sum of the conjugate transposes. This is a very important property. We'll be using this a ton as this course goes forward. The next property that we're going to also use a ton is that AB conjugate transpose is the same thing as B conjugate transpose, A conjugate transpose. Okay, so it works exactly the same way as the transposition that we ended up seeing for the unitary gates, for the reversible gates. And this kind of opens up, well, what's the natural analog of the reversible operations? Because really, all I've done so far is describe what the objects are. Also, I guess I should describe one final thing that ends up coming in, which is measurement. And again, when we have measurement acting on a quantum state, what this will do, and I'm assuming here that this is a measurement in the computational basis. In quantum theory, we often don't restrict ourselves to just measurement in a single basis, but in quantum computing, typically when people talk about measurement, they mean a measurement in a computational basis. And how that works is that basically will end up yielding a copy of EJ with probability PJ. Okay, where the PJ again is formed from the square of that thing. So that's what measurement does. And again, measurement in this case will compress our unit vectors that we have over here to single computational basis vectors. Okay, that's cool. But the next thing that I'd like to show you is what the natural analog of the reversible operations is. And the natural analog, it turns out to be, well, general unitary transformations. And basically what we want is we want all of our operations to be all operations except M are reversible, or sorry, invertible. Okay, so we want all of them to be invertible, and on top of that, what we want to do is we want to ensure that they maintain inner products between vectors. So why is this the natural generalization? Well, if we flip back to our discussion about permutation matrices, you'll note that in the classical case, classical is often what people in quantum will use to refer to everything else that isn't quantum. But in any case, for the classical case, what we ended up having is we ended up having all of our matrices that describe this taking the form of permutation matrices. So all of them would end up mapping one thing to another thing. And so if two vectors had zero inner products, they would remain zero inner products. And we would like to have the generalization of that property, i.e. what we'd like is like for two individual quantum states, we'd like to ensure that if phi and psi are quantum states, and again, they're quantum states if their length, as in their inner product with themselves, squared, is equal to 1. If these two are quantum states, then we demand that the set of legal transformations that we have at our disposal will end up mapping, let's say, U psi and U psi over here. We want to ensure that the inner products between those two are the exact same as the inner products between phi and psi. So let's actually just figure out these inner products. So the inner product between U phi and U psi is going to be this. Because again, we would normally take the transpose in order to be able to figure out the row version of this column vector over here. But because of the fact that they're complex, now in this case, we've also got to do a transpose. And so that's why the T turns into a dagger in this case. And in this case, the inner product is the adjoint of phi multiplied by psi. Okay, but remember there's those properties that I mentioned before? We can use this property over here in order to be able to re-express phi. This is phi adjoint times U adjoint U psi. And this has got to be equal to phi adjoint psi. And Furthermore, we demand that this is true for all phi and psi. Well, if that's true, then we've only got one possible choice for an operation. This operation has to be the identity. And if U dagger U is the identity, then U dagger has to equal to U inverse. And this property over here is the property unitarity. So unitary matrices satisfy the property that U conjugate transpose is equal to U inverse. And the inverse always exists. So this is the kind of like biggest class of transformations that we're allowed. And in quantum computing, really the art going beyond this point over here is to actually figure out ways of taking the transformations U psi that we end up getting and compiling these down to a sequence of quantum gates like G M minus 1 all the way down to G0 acting on psi. So that's what we're going to be doing. We're going to be, throughout the rest of this course, looking at trying to build different types of unitary transformations, arguing about what computational power comes from being able to do unitary transformations on the quantum states, and showing what the distinction is between the classical case over here where we have probability vectors that are all positive, and the quantum case where we can have complex components. And to give you a little bit of a spoiler again for this, the main difference that we end up seeing between the two is that the case where we have the complex coefficients, it actually is going to allow the signs to mix, bringing up interference between the different branches that a computer can go through. This never happens in the classical case. I mean, you can see that because measuring and projecting yourself down to just one possibility really doesn't change the output distribution. But in quantum, because of the fact that these all have different signs, and the sign is lost when you measure, this ends up causing us to reduce. Now, there's another thing, now that I mention it, that I also want to note, is that because of the fact that the vectors over here have this e to the I phi, we run into this issue that, okay, well, let's say we wanted to represent E1 or E0, okay, which for a 1-bit case in quantum land, that's called a 1-qubit case, could be expressed as this. But because of the phase, we can always end up replacing that by e to the I theta, and we end up getting the same thing. But it turns out that for any matrix, if we have something like this popping in, what we can always do is we can always say, okay, well, EK transpose, some transformation, M over here, well, I already used M, G over here, times E naught. That is equal to EK transpose G e to the I theta 1, 0, and we can just bring that out. And so, in particular, I guess if we wanted to take a look at E0 transpose over here, we would end up getting a e to the minus I theta popping out, and those two would cancel. So this property, known as a global phase property, ends up saying that the expectation values that we end up getting are exactly the same, irrespective of value of a phase that we multiply everything through. And so in this sense, what we do is we identify physically E0 with e to the I theta E0. They're exactly the same vector because when we do the adjoin, we multiply two of them by each other. After doing this, the e to the I thetas will cancel. So that's one of the things that is important to note, that all of these vectors are only defined up to an arbitrary complex phase. Now, before I conclude, the other thing I'd like to do is I'd like to give you some examples of unitary operations which would be valid to manipulate quantum states. The first example is one that you're already aware of, the NOT gate. As I mentioned before, the NOT gate in the computational basis is 1, 0, 0. And this is a unitary matrix because, well, NOT squared is equal to identity, and NOT transpose, it turns out to be NOT, and in this case, NOT dagger, because everything's real, is equal to NOT transpose. And so this is clearly a unitary matrix because NOT dagger equals NOT inverse. Similarly, the Toffoli gate, which between if acting on the first two with the target in the bottom one, so this is often drawn as pictorially like this with A, B, and C. Okay, the Toffoli gate of this form has the exact same property, where Toff equals 1, 1, 1, 1. It's going to be a transformation of that form over here. Okay, and you can see immediately from this that this is, in fact, a unitary matrix. Again, Toff inverse equals Toff transpose equals Toff, just like we ended up doing before. Okay, now, final thing is, well, do all unitary matrices have to look like this? And the answer is no. There can actually be some very, very different and important unitary matrices. Perhaps the simplest, very different one that I can think of is the Hadamard Gate. The Hadamard Gate is a unitary matrix of the form 1 over root 2, 1 over root 2, 1 over root 2, negative 1 over root 2. Okay, so Hadamard has the property that Hadamard acting on E0 ends up giving us the same thing as 1 over root 2, 1 over root 2, 1 over root 2, negative 1 over root 2, acting on 1, 0. This is will just end up yielding that column. So that's 1 over root 2, 1 over root 2, or if we prefer unit vector notation, this is 1 over root 2, E0 plus E1. Similarly, HE1, we can end up seeing as 1 over root 2, E0 minus E1. Okay, so what this ends up saying is this gate does something really cool. What it does is it starts in a definite state. It starts in E0 or E1, and then it transforms it into a uniform mixture between the two. And this property is actually something that ends up leading to vastly different behavior for quantum versus classical. And this, in essence, is where all the power of this computational model versus stochastic classical computing ends up coming from. So next time, what I'm going to be doing is I'm going to be talking about a little bit more notation involving quantum. So I've been using this unit vector notation. I'm going to be introducing a slightly slicker notation known as Dirac Notation for dealing with this. That is basically the same thing, but it does a couple of things a little bit nicer, like tensor products in particular. Then what I'm going to be doing is I'm going to be talking about some other important properties of quantum theory. In particular, I'm going to be talking about the no-cloning theorem, which ends up saying that quantum distributions can't be cloned willy-nilly in general. And also, I'm going to be talking about why the order of measurement versus gate operations can matter a huge deal for quantum computation, and they don't matter for a classical one. And so, well, okay, thank you very much for braving another lecture, and yeah, I look forward to chatting with many of you in the next class, and seeing the rest of you virtually in the next lecture. All right, see ya.